Yeah, get going.
Thank you everyone for joining us. Thank you, Peter, for coming. I can say a few words about Peter, although I think many people in the audience know him already. I still think it's worth saying that Peter is a professor from the University of Erlangen and also a fellow of the Max Planck Institute for the Physics of Light. He's also the chair of laser physics. He actually just received the highest German research award right now for 2022. It is considered by many the German Nobel Prize, and we're really glad and happy for the opportunity to host him so quickly after this really important award. Peter has an ERC advanced grants, and before that had a consolidator one, and many more big important awards and grants. He also leads together with Bob Byers the Accelerator on Chip community, the HIP community. We are really glad, many of us, to be part of it in different ways and to join the conferences that it is organizing. But on a more interesting anecdote, I saw that Peter has a military service record in his CV as a navigator on a frigate MDAN, as an instructor in a Navy school. So I think for us it's especially interesting as an anecdote. It's a really cool, really cool thing. But more important than that is that I'm really glad to say that on my behalf and many other people here, that Peter is a really good friend of us and a collaborator on really fascinating projects. And for this and many other reasons, I'm glad to have him give a seminar in the Technion. So Peter, the floor is yours, and I'm looking forward to hear more.
Ido, thank you very much for your very kind introduction. Let me share my slides. Here we go. Yeah, thank you again, Ido, and thank you, Gadi, and everyone for inviting me. It's fun. You talk about military. It's interesting that at the last, what was it, Oasis conference in Tel Aviv, I saw military personnel. Of course, when I see a Navy uniform, especially Navy, I always somehow feel connected. So that is fun. So great. I'd like to share, and of course, I should say this talk was scheduled for June. I blew it because I just forgot about this 1 hour time difference, and I mentioned it already. I owe you lunch for this. So this time I thought I'd be there in presence and I would pay for the lunch. Now again, Omicron somehow killed this, but I won't forget it, and we'll manage, and we'll have a chance hopefully later this year. So let me show you where we stand on our quest on nanophotonics-based particle acceleration. And Gadi pointed out that this is the Russell Berry Nanotechnology Institute seminar. So I should really make sure that I focus on nanotechnology, which I will. I briefly also touch upon, I know you have a big other quantum seminar. There will be 2 or 3 slides on the quantum aspect, but really only minor. But of course, as you kindly pointed out, Ido, there are so many great friends and colleagues in Israel, some from the quantum side, some from the nanotechnology side, some of course on either side. So, but here I really like to focus on the nanotechnology aspect of what we do. And what we do, sorry, I should say, what I basically would like to show you and introduce to you is this beauty of a nanostructure. It's a silicon that we etch down 3 micron high colonnade structures of silicon, so pillars arranged one after the other. And I would like to show you what this is for, because this can really take us to build the particle accelerator on a chip. And I'd like to show you where we stand on this quest. So when we think about particle acceleration, we as scientists probably think about these big machines, and you all know them, and you wonder, why are they so big? Well, they're so big because our friends in the particle physics business, of course, somehow request that we deliver them particles with a certain energy. And you know, the Higgs particle has been discovered. Now everybody would like to have TeV energies to do Higgs spectroscopy. The particle accelerator community has done a great job over the last close to 100 years, ever since the invention of modern particle physics, particle accelerators. They now managed to accelerate particles with a gradient of 30 mega electron volts per meter. That's like applying 30 million volts over a meter plate capacitor, starting an electron here and then it has over here an electric energy of 30 mega electron volts, and then the gradient is just 30 mega electron volts per meter. So that's a very, very sizable and very impressive number. It took decades, as I said, almost a century to develop it. And it always amazes me that we as a world are courageous enough to build these big machines just for science. So this is the ILC that is still being discussed if Japan is going to build it. Of course, it's an international project with the support of the entire world. It's a 30-kilometer long machine. You do the math. If you just divide 1 TeV by this gradient, you arrive at 30 kilometers. But there's also many more accelerators out there. You all know these L-shaped machines that scan around the body of a patient. Why are they L-shaped? Because there's a 1 meter long accelerator inside. Why is it 1 meter long? Because our friends in the hospitals need sufficiently energetic X-rays to irradiate tumors. And to generate these X-rays, they roughly need 20 mega electron volt electrons to be slammed into this metal cathode over here. So that's why, same gradient, roughly 20, 30 mega electron volts per meter, they need to be 1 meter long. And this is a big market. We as a society are getting older and older. So every hospital has these machines, and it's really interesting. The linear accelerator for radiation market is valued at $3 billion US dollars. That's a large number, of course. And there are many, many accelerators of this kind being sold these days. How do these accelerators work? They work exactly like this surfer here is picking up energy from this wave. We generate a mode, an electromagnetic field mode, that continuously imparts momentum into the wave or into the particle to be accelerated. In a classical accelerator, this is done with the help of these microwave cavities, where then the particle beam just traverses through. And it's interesting to realize that it's really the breakdown of these cavities, the surface breakdown, that limits the maximum gradient. So surface breakdown for these very, very specialized niobium, usually niobium superconducting cavities, is something like 200 megavolts per meter. Also a very impressive number, 200 million volts per meter fields at the surface of these cavities. And in the middle of this channel, that then leads to gradients roughly, well, that number maybe still a little bit less because the electron is not propagating at the surface, so maybe 100 mega electron volts per meter, give or take. And now you all know that we can shoot very powerful lasers through glass. So what if we go away from metal, but go to glass, and go away from microwave driving frequencies to optical? And that's the idea. Can we do exactly the same? Can we generate a mode like this wave is propelling the surfer, now not at microwave frequencies, but at optical frequencies, and just accelerate electrons? And this structure that you see here is a transparent structure. It's made from silicon, but it's driven with 2 micron light. So 2 micron light just go through the silicon. But this structure then generates near fields that generate a mode that continuously propel electrons through this purple channel here. And what's really, of course, well, it's not surprising, we all know it. Glass can hardly be damaged with laser beams. You need very, very intense laser pulses to damage glass. You need roughly 30 gigavolts per meter to damage glass. And it's this factor of 100 larger damage threshold that should allow us to reach a factor of 100 larger acceleration gradients. And this is really what we want to take advantage of, build much smaller accelerators, just because the damage threshold of glass is so much higher than the damage threshold of these RF cavities. And that means we have to resort to laser beams that power these structures. But of course, you all know highly power efficient laser beams can be generated. And let me show you where we stand on building a particle accelerator on a chip. First off, how do we generate this mode? What's the deal behind it? And almost 100 years ago, these two gentlemen invented the principle of all modern particle accelerators. Just imagine these are cylinders here, just a cut through cylinders. And then back then the question was, how can we generate electrons to high energies with a limited voltage available? So initially they always just try to increase the voltage, the plate capacitor. When you increase the voltage, of course, the energy of a particle that arrives over here from rest and zero energy would then be just higher by the voltage. But then they realized we run into hard issues. You can't really generate voltages much higher than 1,000,000 volts. But of course, how do we generate larger particle beam energies? You just go to an alternating voltage. When you have an alternating voltage, You just have to make sure that you switch the voltage every time the particle is hidden. So here, the particle is accelerated, then it's hidden in this metal cylinder. When it's hidden here, just swap the field between these two cylinders here, so that when the particle arrives here, it also sees an accelerating voltage. So what you do is you just have to manage to swap the voltages phase synchronously with the particle's position or particle's momentum. And this is exactly generating this mode that continuously propels the particle. That's the main scheme of almost all particle accelerators out there these days. And the question is, does it work with optical fields? Well, you all know we better shoot the laser from the side because the polarization of the laser is perpendicular to its propagation direction. So that's why let's have a laser shine in from here. Then a particle can be accelerated, but half an optical cycle later, the particle is decelerated. And you can show analytically that for a purely oscillatory field, the effects of acceleration and deceleration just fully cancel. But only in free space. What if we go to the close proximity of, for example, a glass structure? Watch what happens here. The glass, of course, has an index of refraction larger than 1. That means the light travels more slowly here than here. So the light has just traveled a little further here than over here. So now you have a corrugated phase front that just propagates up here, and the particle comes in here. So over here, it feels an accelerating force. Now the particle continues, the light continues, and half an optical period later, it happens so that the particle again sees an accelerating field. And so this is the effect of this structure here. So in the vicinity of a nanostructure, we can just manage that a particle always sees accelerating fields. What you do is you basically rectify the field and the frame co-moving with the particle. You can also express this slightly different. We can just really look at the near fields. We look at the field that is synchronous with a particle, that moves with a particle in one direction. And then you see that this near field has accelerating components, like shown here, these yellow or reddish ones that just move with a particle. It also has decelerating components, the bluish ones here. And what's important, it also has components that point towards the surface. So the particle injected here would continuously be accelerated towards the surface or away from the surface over here. So you always have transverse forces at your disposal, which will be interesting later to steer electrons also, not only to accelerate them. The big catch about this scheme is also already indicated here. The mode that you see here is an evanescent mode. You can show it with a couple of lines that the field has to decay very quickly away from the surface. You see it here by the color. At the surface here, you have a dark color, meaning large deceleration or acceleration. And as you go away from the surface, this mode that propagates along the surface just decays very quickly, basically on the scale of a wavelength. And that's why we have to bring the particles very close to the surface, or we have to make very small channels. That's a big catch of this scheme. We can discuss later how badly it affects us. There are many structures out there that have been conceived to basically efficiently generate a mode that can propel electrons through these structures. I'm going to mainly show you variants of this structure here. We see it's kind of a binary grading structure. You can also just take this material away, then you end up with these colonnade structures that you've seen. And for non-relativistic particles, also single-sided structures work. Let me show you that this is a very, very old idea. It's really interesting to realize that, for example, Shimoda, but also other, realized right after the invention of the laser, even before the acronym laser was coined, it was still called an optical maser, that, well, now you have this basically very nicely, very well-confined beam that can be potentially high energetic. Why not build a particle accelerator from it? So right after the invention of the laser, Shimoda had already the idea to build a particle accelerator using the optical maser. In the same year, Lohmann, back then at IBM, and it's a fun historic fact, he actually, from IBM in California at Almaden, he moved here to Erlangen and became the chair for optics. It's a fun connection between California and Erlangen, which continues, as you will see. He already in 1962 patented this scheme where you have some kind of corrugated structure here that generates a mode, and it's exactly the scheme that we are using. You see here, this is from his patent filed in 1966. Let's say he was probably 50 years too early, but better be early than later, right? As we all know. That's interesting to see. Then these gentlemen here, interesting enough, at Hitachi Research Laboratories, demonstrated that this effect works, and they demonstrated it with a metal grating. So they fired laser, excuse me, not laser, but basically today we would say terahertz fields. Back then they called it millimeter radiation. They fired terahertz field at the metal grating. Of course, a metal grating is also easily damaged, so they couldn't really reach high gradients. They reached kilo electron volts per meter, but still, it was the scheme at terahertz field was demonstrated in the 80s. Then in the 90s came some great ideas by Jamie Rosenzweig and also Bob Bayer. Hey, let's go to dielectrics. We only need to basically touch the phase of the field. We don't have to have any metallic properties. Dielectric will do the job, and that really then opened the field towards GeV per meter gradient acceleration. Bob Bayer's group, together with the late Bob Seaman, who was an advanced accelerator scientist at SLAC, teamed up and showed some fundamental experiments then in the 2000s. Also, for example, already production and characterization of attosecond electron bunch chains. I'll come to that in a minute again. And it was then when Bob Bayer and I met, we were in neighboring buildings. I was working on a new electron source based on femtosecond laser pulses. And Bob Bayer heard about it. I still don't know how he heard about it, but we met, and first thing he said, "Peter, I need your source." And ever since then, we teamed up to build the particle accelerator on a chip. Before we go there, I show you the team, let me just show you what we did after I had returned to Germany and Bob's group had continued at SLAC. We were already formal collaboration partners, and we were super happy that basically simultaneously, my group at Erlangen could show that this effect works at optical frequencies with a glass grating. We used a 30 keV electron beam from an electron microscope, and the Stanford and SLAC group used a beam of relativistic electrons, 60 MeVs at SLAC, something like an 80 meter long accelerator, whose output they focused into such a structure. And it's fantastic to see that it worked right away at relativistic frequencies, but energies, but also non-relativistic energies here. And then we teamed up. We were very happy that the Gordon and Patty Moore Foundation supported our proposal to build the Accelerator on the Chip international program. And it's fantastic to see. So we have all kinds of experts on board that we need. We need the nanostructures. You'll see more about them soon. We need simulation experts, particle accelerator simulation experts. We're very happy to have them. We need light coupling experts. You will also see that in a minute. We need electron source people. We need the system integration. And we're also very happy that we have relativistic experts for relativistic beams on board at SLAC, at DAISY, at PSI, and in Switzerland, because we also want to show that we can do something with these nanostructures at really high energy electrons. And what's really absolutely fantastic, we have really, meanwhile, gotten more and more people on board. Ido's group is doing a fantastic job here, and we're very happy to have Adi Ari from Tel Aviv University on our HIP Scientific Advisory Board. Our Scientific Advisory Board is really extremely helpful and help us guide the program. This is the last collaboration meeting in Hamamatsu, Japan, before Corona kicked in. Because it wasn't Japan, not everybody could go. So we have more people. This is Bob Bayer here, you see Ido, other people on board. And this was the first, well, almost post-Corona collaboration meeting. You see, it's not really post-Corona, but screw the masks. People look much nicer without, right? And of course here, this is Adi, Ido over here, Roy Shilo, my fantastic postdoc. Was a great meeting. Now, next meeting was planned to be in Israel in March. We'll probably only have to have it, can only have it in May. But let's see, hopefully without any mask. So where do we stand? We have now all individual functional elements to build an accelerator. To build an accelerator, you not only need the acceleration components, I will show you more about it, you also need to be able to deflect the beam, because the beam will never be staying on track. You always have to be able to steer it. We have shown that we can accelerate beams in subsequent interaction regions. We can focus the beam by purely optical forces. And we have these high brightness electron sources that you need to inject the beam into this very narrow channel here. Here you see it again. So this is basically this colonnade structure that serves to generate the near field. We shine the laser light from one side or from two sides. And then these basically minimal amount of matter suffices to generate the near fields inside of this channel here, into which we focus the electron beam. But an accelerator is much, much more than that. It's not sufficient to just use one element, as you all know. You really have to make sure that you not only accelerate, but also keep the beam on track. So you have to confine it, not only for technical reasons. You all know when you push something very hard, when you exert forces, there are always other forces, basically dictated by Earnshaw's theorem, that drive the beam apart. So you really, it's not only a technical issue, it's physics. That you really also have to make sure that you confine the beam, keep it together. And so the modern way of doing this, for example, in ion accelerators, is this way. You switch between accelerating sections and confining sections. And I'd like to show you that this works. The acceleration we haven't shown, but I want to show you that we can now actively transport a beam through such a device. And people in the accelerator physics business always say before acceleration comes transport, but then it's only a small step from transport to acceleration. So we're very excited about this. Before I do so, let me just show you what else we have achieved. Sorry, I should say. So this beauty of a structure will do this job. We'll come to that in a minute again. But let me just show you where we stand in terms of integration. That's also, of course, really interesting. So here's the acceleration structure. And ideally, of course, we would just feed the laser light on with a photonic chip so that really everything is integrated. We don't need any free space optics. This is a proposal here from Tyler Hughes from Xiaoyu Fun's group. And let me just show you what our Stanford friends have already shown by integrating everything on a chip. And here's something that's I think really fascinating, and I want to spend a minute on it. That is this inverse photonics design. I'm not so sure if you've heard about it, but I'm going to show you now these structures that you would probably not come up if I gave you a piece of paper and a pencil. So here you see something periodic, but you see there are many, many details here that almost look like some biological, well, something living, right? Or some cell or something. That you would not be able to just sketch when you know, okay, it should be periodic to fulfill this phase matching condition that I've alluded to earlier. But then what about these details? And these details you get from what people call inverse photonics design. It's just a numerical tool that tell you the best boundary conditions for a certain field configuration you would like to have. And inverse photonics design has been co-invented also by our Asia group member, Jelena Vukovic, as well as Xiaoyu Fan. And they've done fantastic stuff, and we now use it to really come up with photonic nanostructures that do something just better than you would do it if you would pencil it. And here's one. So here you see an inversely designed photonic structure that accelerates electrons in this channel. And then they're grading couplers. Sorry, I should show. This is then this channel on this chip. And then here, they are grading couplers, here and here, where you can just fire laser beams. Then the laser beams are coupled into the waveguide structure here, propagate in the waveguide to this accelerating channel, and then accelerate the electrons. And this works. So Stanford partners have shown this. Here, show this beauty of, so you see this beauty of a chip again. You see this waveguide structure here is also, this grading coupler is also pretty complicated. It's designed with the help of inverse photonics design to just couple in efficiently relatively broadband laser pulse with little damage to the structure. And this you can all do with this inverse photonics design. You see, you really have to have your nanofabrication under control to design these fine features here. It's really the fine features, the finer the features you can make, the better your structures. And it's really the fine features here that, for example, set the maximum acceleration gradient. So here, nanotechnology, nanofabrication is absolutely utmost priority to have this under control. What they showed is then that they can accelerate this on-chip waveguide fed DLA structures. I don't want to go into detail here, but it works. So that's great to see. We can really also go towards integrated coupling. And let me also show you that we did something, Ido's group and my group, with the help of this inverse design. So here you see a channel for which we send the electrons. And then initially, we just didn't give any design, but we just asked our computers, we want the highest coupling between an electron that propagates through here and laser fields. And this is what inverse design does for you. It comes up with a structure that you can easily identify as a resonator, right? These are Bragg mirrors. So we will just get field enhancement in here. So we get a nano resonator that the inverse photonics design has designed for us. Well, you could come up with something like that, but the exact shape here, so it's not so easy to find. And it's clear, you already see, we shine the light from here. So it's even an asymmetric resonator with high reflectivity over here, lower reflectivity over here, that we get for free. Not really for free, inverse design does it. Of course, you have to program the inverse design, but then it works and you get this beautiful structure. Does it work? Yes, it certainly does. So here you see an electron microscope image of this structure. The electrons come in from over here. They're shot into this narrow region here where they propagate through. We shine the light from the side here. And because the coupling was so high, these people here, and you know pretty much everybody here, I guess, on this author list, managed under Ido's fantastic leadership to really show that once you have this coupling, you can now take the electrons and measure quantum statistics of the light. I don't have time to go into detail here, but it was fascinating to see that we could clearly distinguish between coherent light, where we see a beautiful coherent interaction, and thermal light, where the coherence is gone, and we see it in the electron spectrum. It's really beautiful. It relates closely to this photon-induced near-field microscopy that's been pioneered by Ahmed Zewail and with fantastic work from these groups here. I've seen another big player in the audience, Ofer Kfer, I think was in the audience, who did fantastic work in Klaus Rupper's group on this field, which is called, Zewail introduced it as photon-induced near-field microscopy, but it's now much, much more than microscopy. It's really coherent electron-free light coupling, and I think it will still allow many, many more beautiful things to be seen. Just one slide on this, because my fantastic postdoc, postdocs Roy Schilo and Thomas Schluber showed for the first time that you can also have this quantum coherent interaction between an electron beam and these laser pulses and an SEM. An SEM looks entirely different from a TM, as you all know. It has this large sample chamber. You have lots of access to the electron beam. You can not only have one nano object here, we also just, like everybody, placed a tip, but you can also have anything else. But we could just place many more. You have so much room here. First off, we placed the spectrometer just into the SEM chamber because it's so simple. This is what Roy designed. It's a custom-made high-resolution electron spectrometer. Many people ask us, guys, did you patent this? We're not sure if we can still patent it, because if you will, it's just a high-resolution spectrometer and many of the details are already out there, but still, Roy did a fantastic job in designing it exactly to fit in here. So it's small, it fits into this chamber, and it allows us to measure these electron spectra where you also see these photon orders. So this is just energy. This is the energy of the central beam. And when we then have the electrons and the light field interact here at the needle tip here and the surface at the near field of this needle, we just see the quantized interaction. So here you see these photon orders that beautifully show up in this low energy electron beam. So this was at 17 keV, 17 keV, much, much lower than the TEM energies, which will allow you other insights. And definitely it will allow using with this quantum coherent coupling of light fields and electrons in a much simpler setting. So we can just use an SEM, and you'll know you can almost get an SEM for free. If you're lucky, you get it for free. Well, you also get TMs for free, all right? But it's definitely easier to work with an SEM. Here you see more of these photon orders that we could measure at the near field. of this needle tip here. So we really think that this could take this spin physics and really expand and make it available to a much wider range of researchers. Let's go back to the particle accelerator on a chip. Let me just show you that our friends at UCLA, the group of Pietro Musumeci, has taken an 8 MeV Linac, so mildly relativistic electrons, and they fired these electrons into a double grating structure that you can see here. Nothing fancy, not inversely designed, but what is fancy, it's made from glass, and making these structures from glass is always hard. And what they could show is that the structure could withstand incident fields of up to 9 gigavolts per meter, which is already great. And with this, they could demonstrate peak acceleration gradients of close to 2 giga-electron-volts per meter. So this was, of course, really fantastic, because exceeding 1 GeV per meter is a fantastic result. And it really means that we can build these accelerators very small, just because we've already generated or demonstrated this very small gradient. There's more. There's much more than acceleration. You've seen initially that we modulate the energy depending on where within a single cycle of an optical field the electrons are injected. So imagine this is a single cycle of the field, and at a certain phase value, the electrons are accelerated. For another phase, the electrons are decelerated. Now, what happens if you do this? Then these electrons really become faster, because in our case, they are non-relativistic. So these guys catch up with these guys. So after free ballistic propagation, we just see that the electrons arrange in a very small region in time or space, which can be, for example, like shown here, much shorter than an optical period, can easily be on the 100 attosecond range. So let's see if we can do this. So now we build a structure. You see a top view here. We made these pillars again. This here is a Bragg mirror, so that we only have to shine laser light from one side. We only shine the light from one side. If you place the mirror at the right distance, then the back reflected beam just gives us a symmetric mode in here. And here, this structure we call the buncher, exactly because of this, because we imprint this energy modulation. And this energy modulation after free propagation, and so there's just nothing here, we just let the beam propagate, should then lead to this bunching behavior if we do everything right. So here we put what we call the analyzer. It's just a copy of this structure, and we can now fire laser pulses here, and then we fire a copy of the laser pulses here, and we just time delay them, and we can record spectrograms. So we just record energy spectra as function of time delay between these two pulses. And the results are a bit complicated. So when you just get the experimental results as function of this phase difference, they are not so easy to interpret. So you just run a numerical simulation, very easy point particle simulation, and we just compare what we see here. And you see that our simulation results match the experimental results pretty well. Now we can just read off what happens here. Sorry, I should say what we do here from top to bottom. We increase the field strength in the buncher. So we just increase the field, the bunching field strength in this first section. So initially here for these very weak fields, we see from just looking at our simulation results that we hardly see any bunching, a little bit, but not so much. Then here we see this is the ideal field strength. At that section of the analyzer, we get the shortest pulses. So we can really we can look at this, really analyze this well here, also quantitatively, and from this nail down that here we have electron bunch durations, or bunchlet durations, I should say, of 270 attoseconds plus minus 80 attoseconds. The error bar comes from a careful analysis of really image comparison, if you will. Then in phase space, this looks really like this. It just shows you that the fast electrons have just now caught up with the slow electrons, so that they all arrive at the same time here at this analyzer structure. And then here, the fast ones have already passed the slow ones. So here we see overbunching, and we get these double horn structure where we have non-ideal bunching again. So this works. It's nice. We have phase-space control, but it's a first step. It's not really complex, right? But still, it's nice. Let's try and see if we can exert much better phase-space control over these electrons. So look at this beauty of a structure. It's 80 microns long. The channel width is just 220 nanometers. So it's already pretty high aspect ratio structure. And what we do is we just fire the laser pulses from the side like before, inject the electron beam here. And what we'd like to show here is this transport. We just like to show that we can transport electrons through here. And how does it work? Let's just look at this force that's acting on these electrons, the force of this co-propagating mode that's acting on a co-propagating electron. You can see here it has a forward component, so the z direction is the forward component. This is the acceleration component. It's plotted here in whatever the color is, turquoise, blue, and it just has this behavior. So the cosh in the transverse direction. So it doesn't really matter. Actually, yes, it does matter. Let me show you. So here we plot the force in the forward direction. And you see here, it behaves quite smoothly. Here, for example, the electron is accelerated. Here it's decelerated, and it's just modulated with a sign depending on where the electron sits in the phase that accelerates the electrons. It's either accelerated or decelerated. Now there's also the transverse force. So the force in this direction, perpendicular to it. And that's why this equation is important, because here you see how these two forces are related. So whereas the one is modulated with a cosine longitudinal direction. So for example, maximum acceleration here for a design phase of 0, we see here that then the force that basically deflects the electron is 0 here and has this behavior. So now watch what happens if, for example, we place ourselves here. It means that the later particles feel an accelerating force, the early particles a decelerating force. So that means that longitudinally, the bunch is compressed. It's good, you want to keep the bunch together. But then laterally, the particles are driven apart, because what I'm plotting here is the force that acts for a particle slightly at negative x values. That means if the particle is already slightly off the center, it feels an even further force down, and the same holds symmetric up. So laterally, the particle bunch is being blown up. That's not good. So that means we just lose the particles very quickly. But watch what happens at this design phase. Here, this lateral force keeps the particle beam together. It compresses it. But then the longitudinal forces blow the beam apart. So that's bad. So what do? It's well known in accelerator physics that you just have to toggle between these two positions. You just toggle between these two positions, and if you do everything right, the net force will keep the beam together laterally and longitudinally. And you can even extend this to 3D, to the third dimension, out of plane here, which we here in our first experiment just leave out. But it also works in 3D. The most important point is these field components are always present, and you can't really play with the relative phase of them, but you can play where you place the electron, if you place it here or here in your design phase. How do you do it? Or how do you jump between these two positions? Well, you dial it into the structure. You just have gaps in the structure here. When you have a gap in the structure, the particle continues to propagate, but you have a phase shift in the optical mode between here and here. And that's why when you have a jump here, the particle jumps between one phase to another phase, and to another phase, and so on. And you can this way jump between these two regions in phase space here. We don't have to go into this here. This is exactly what this structure is designed for. You see these gaps here. These gaps you really have to hit the right size. Turns out that making the structure was, on first glance, easy. Turned out that we really needed 10 nanometer accuracy in making these structures. Only then they worked. Otherwise, the fields are out of phase and nothing really works together. So that was fun to see, but in the end it did work. So we now have 10 of these phase jumps here, one every roughly 7 microns, corresponding to roughly 80 femtoseconds. As I said, for this to work, you really need to get the fabrication right. And clearly, if this works, 10 phase jumps, where you really do interesting operation in electron phase space, we will have complex electron phase space control at optical frequencies. Does it work? So what we do here, we now just inject electrons into this structure. When first we just measure the current without any laser field, and then we just switch the laser on. And what we see is these orange data points And particle tracking simulation is this blue line here. And you see the current increases. So we get more and more electrons through when we increase the laser field strength. That's great. This is exactly what we wanted to see. This is this transport. We just make sure that we can confine the electron beam with these complex optical forces, and the data match our simulation results really well. Then, of course, we also wanted to show that we can overfocus. So you can, of course, exert forces that are too strong, and then you actively kill the beam. For this, we had to use another structure because here we were damage threshold limited. But with a slightly different structures, just longer macro cells, I'll show you in a second, we could also show that when you increase then the laser field above the ideal guiding field, that you even get fewer electrons through than without the laser, which is 1 here. So we can actively kill the beam. This is how it looks like in very simple classical particle tracking simulations. This is for the ideal guiding field here. You see we lose some particles at injection, but once they're injected, the ones that are injected are really nicely guided through here, through this long structure. And don't touch the colonnades anymore. You see when they come close, there are optical forces that drive them back, and then here they come close, optical forces drive them back. So this works. And this is this overfocusing structure. You see one of these cells is now longer than here. And then the forces act for a longer time. So just watch what happens to this orange trajectory, for example. It basically gets a kick over here. And now it should get a kick back here. But it just doesn't come early enough. So it's basically, it gets a too large kick up here and it's just lost over here. And that's why you see here, we can also observe this overfocusing effect. So this works, we're very, very happy because now it's not a big step. We basically have to play a little bit with the structures to make them from a transport structure to an accelerating structure. And this is exactly what we're working on these days. Just to show you a simulation that our collaboration partner Uwe Niedermeyer did. Here you see what happens in phase space and what happens to the energy of a particle if you just modify the structure slightly. You see here this is the longitudinal extent of the electron pulse, and this is this extent in transverse phase space. And you see how we basically control or allow the particle to spread laterally, shown on the right panel here, and also to spread longitudinally. But you see it's always somehow out of phase. We allow the particles to spread, then we confine them again. And when you do everything right, you have this control that you hardly lose any particles, and on top you can even accelerate them. And this works now up to 1 MeV. We're very, very happy that this really works with realistic beam parameters and only 7% particle loss. This is of course theory, we have to show it, we're working on it heavily. We really hope that we can show some results soon, but unfortunately we are not there yet. But we're very happy because these simulations, or so far the simulations when we have the right structures, really match to what we see in the experiment. So we are quite optimistic that this should also work. Where do we stand? Clearly, this is lasers and nanophotonics that we have to bring together here. And this historical perspective is an interesting one because you probably know that even though accelerators, classical particle accelerators, had already been invented in the 1920s or so, or even earlier, even in the 19th century, this field really took off because of a very important invention that was made for another reason. It was radar klystrons, right? So klystrons that were invented for military technology that then also were taken over. It was just a power efficient energy source that then drove accelerators, and that really only allowed us to build these big machines that we have seen, power efficient particle accelerators. And we believe that with the power efficient fiber lasers that are now ubiquitous, we can really build a particle accelerator on a chip. And Bob Bayer calls this a stealth technology. Maybe this will develop into a technology where people don't even know what's behind it anymore, because it can be fully integrated like the laser. We all know the lasers are everywhere and people don't even know what it is. They use it. It's just a stealth technology. So why is this interesting? We believe that we can come up with new radiation therapy instruments where basically on a tip of a pen. Oh wow, this is interesting. Check this out. My hand is on focus, but the pen is out of focus. So I'm showing you a pen here, but you don't see it. Zoom is doing a good job, I guess, or not so good job. Anyways, on the tip of a pen, we hope that we can just build a particle accelerator. So this is how it's supposed to look like. We just have a fiber, and of course we need some electrical connection here to have a particle source, electron source on a chip, where we do the acceleration on a chip in this small encapsulated thing that should fit on the tip of a pen. And of course, then a physician could just bring it and do some proximity tumor treatment. And electrons actually are really good if you bring them close to a tumor. Now we use ions because the ions first have to go through a body to the tumor. Then you use the Bragg peak for the ions to absorb their energy. Here, with electrons, they absorb right away. So if you can bring something close to a tumor, electrons are the particles of choice. So that's interesting to realize. That's, of course, a far-reaching goal, but it could be a great dream. But once you have that, you can even come up with new options with pulsed beams. Of course, we've shown it. I didn't have time. We can also go back. We can also convert the electrons again into photons. We've just done it. We can come up with beautiful inversely photonics design structures to then just build Smith-Bessel radiators, where you just take the electron and convert them again into photons. The beautiful thing is they're automatically ultra fast. You can even dream of some compact free electron lasers. And we can also dream of new electron sources with fantastic time structures. Here I'm only writing sub 10 attoseconds, but we believe that we can even do sub 1 attosecond pretty much right away if we wish to. If there is any use, I think we can really generate zeptosecond electron pulses very soon. Why is this interesting? Because we believe that we can probably offer new tools that are university lab sized, that for if, of course, they're out there, but you need to go to big facilities, and maybe you can do material science, structural biology, also now at a much smaller lab, with, of course, much smaller flux than at the big machines, but still, everybody could do it in their lab. With that, let me thank my wonderful group. This approach, this 8-chip accelerator on a chip program on our end, is really headed by my fantastic senior postdoc Roy Shilo and his junior colleague Tomasz Gruber. The two of them, fantastic team with several more people. Others here work on other experiments. I've only shown you this accelerator on a chip project. I didn't really have time to comment on the fundamental questions we, together, for example, with Avi Gower and Yiming Pan, we have been addressing recently. But this is extremely interesting to see that this wave packet nature of the electrons is also central here. I'm just saying it because it doesn't even show up here in my summary and outlook, as I just realized. But I wanted to show you how important this nanophotonics aspect is. I just wanted to show you that when you can make these structures here, such beauties like here, and interesting enough, this image won a image competition by Oxford Instruments because they thought it's so beautiful. And it's actually not easy to make them because they're 3 microns high. My postdoc, my former PhD student, Payman Yosefi, who's now a postdoc at another institute, has developed this recipe to etch them 3 microns high. And this really allowed us to do all these experiments, which were demonstrating all the individual elements we need for an accelerator. Our friends at UCLA with other structures, but still have shown 2 GeV per meter. The Stanford group has shown waveguide integrated feeding, which is important for the future. And this inverse photonics design, I think that's important, cannot be overestimated. It will really help us to go to entirely new fields. These you see are still the old pillars, all the old pillars that you see here. This is the new structure. This is inversely photonics designed, which already reached much higher coupling between electrons and light beam. We could demonstrate net energy gain. I didn't really have time to discuss it. It's not so important at this point. Definitely, we could show, and I think we hold the world record for the shortest electron bunchlets. So 260 attoseconds, I believe, are the shortest electron bunches out there. We could show this complex electron phase space control in the form of so-called alternating phase focusing. And yeah, where is this going? Soon we hope to achieve serious energies on a chip, 1 MeV. We could definitely do attosecond, if not zeptosecond, electron-based imaging. So, for example, laser pump, electron probe. This is closely related to what we've discussed with some of the gentlemen I just mentioned, where the wave packet nature of the electrons, of course, also plays a very important role. New light sources can be on the horizon, maybe even new medical devices. And very soon we'll hope, actually we don't hope, we do already, experiments at DAISY and at PSI with these ultra-relativistic beams, just to show that these nanostructures can also do something there. For example, we want to measure how short these pulses are that, for example, Swissville can generate, because they only know it from simulations. They don't know how short the electron pulses are, and we want to measure it for them. With that, thank you very much for your attention, and I look forward to any question you may have. Thank you.
Thanks, Peter, for really a wonderful talk. I'm really fascinated by those topics and by the stuff that's being done, and I think I'll open the floor for questions. I have a few more from my side. Maybe Avi, you go first, because I see your hand raised.
Okay. Peter, thanks very much for this beautiful presentation of an excellent research show.
Thank you, Avi. Quite something when you say this.
Well, it seems that you achieved the goal of getting energy acceleration, but many of the applications that we would like to have require also higher current. How much current can you pass through these narrow channels? It's very little. Now, specifically, I wanted to ask you, I saw the recent archive paper looking at the limitations of having more electrons per pulse. The limitations are basically due to Coulomb repulsions near the cathode. And you have done these experiments with femtosecond lasers. And I wonder if you would use picosecond pulses, would you be able to get more current, or other ways to get more current through the structures, higher repetition rate, or what do you envision the way to get more fluence from such a DLA accelerator?
Thank you, Avi. You put your finger right into the point where it hurts currently, clearly. So that's, I think, the most critical, really, it's the critical point for all the applications, as you point out. But you already mentioned several excellent approaches. So higher repetition rate is definitely the way to go. We can go there. You probably know that there are commercial lasers out there now that deliver a femtosecond, or also, as you suggest, picosecond pulses easily at megahertz, if not 10 megahertz rep rates. We believe this will scale up. The power scalability of these systems is amazing. So this will certainly be a viable approach to go up with a repetition rate that drives up the average current, which is important for many of the applications. If you also would like to have higher pulse charge, then you could try to make the channel larger and simultaneously make the wavelength, make the optical period longer by going to longer wavelengths. So currently we work at 2 microns, but maybe it's not the ideal wavelength. Maybe 5 microns are better, I don't know. What's extremely interesting, and it has just been theoretically really investigated in detail by Jin Jin from Shanhui Funds Group at Stanford, is we don't have to just etch everything away and leave a single channel here, but we can, of course, just copy. It's really literally copy and paste in the design process, and just have many of these accelerators next to each other. So we can have many acceleration channels next to each other and accelerate in parallel. And this could even probably work in 3D. What's also very important, and we're working on this, but it's the hardest part. Everybody knows it. When you can work with optics, is great. When you have to work with electron optics, everything takes at least factor of 10 longer. The sources are pretty good, but the optics between the source and the channel, the acceleration channel, is not good enough. So ideally, you scale everything down. Ideally, you put the source on the chip, because then the electron optics can be much smaller, and aberrations scale with system size. So when you make your system size smaller, you're not so much limited by aberrations. And then you can get also many more electrons into your channel. That will be the electron optical approach, which is probably also very important. If you want to go integrated, of course, you have to put your source into the chip. There can be all of this should help us in getting the current up. So you're right, we need larger currents. I'm very, very happy that for many of these fundamental experiments, especially also with you, nobody cares about current, and we can do beautiful physics even with low average currents. But of course, for applications, this is absolutely crucial. And it's interesting. We've been approached by Siemens, you know, big company here from Erlangen. Siemens Healthineers, the medical branch of Siemens, is in Erlangen. And they just read a press release. So usually we don't talk too much, right? You know about, they are very close, but still there's a big wall between science and academia. They saw this and they find it very interesting. And the numbers they want are many orders of magnitude away. But they said, keep working on it. We still work with the same concept of an X-ray tube that was invented by Wilhelm Conrad Röntgen. When was it? 1890 or so. It's the same concept. So take your time.
They have the patience for
exactly.
Yeah.
So thanks, Avi. Well, definitely we're working on it. We're working on it. It's a lot of development. And because there's so much beautiful physics out there, of course, everybody would love to do the physics and well, do some development on the side, but we all know it's needed. It's needed.
Awesome. Offer, I see you have a question too.
Yes, actually two, but I decided to raise just one hand. So I guess it's like the third time I see this talk, so I go to in the more fringe-oriented questions. But again, it was a very good talk. I was wondering about the inverse optics design. So do you make it are you required to make it somehow stable, that it's not very sensitive to the parameters when you actually fabricate it? That's the first question. And the second, can you actually maybe elaborate and say a bit more about is there an effort, or who's doing an effort to actually make compact and suitable electron sources for that injection into your channels?
Yeah, thanks, Ofer. First point, that's so nice about this inverse design. You can basically tell the code that you, for example, want to smoothen everything with a certain kernel, and the kernel size you can just take from your fabrication capabilities. If you know you can make features with a radius of curvature of, say, I don't know, 5 nanometers or 10 nanometers, you take a kernel size of 10 nanometers, round it off, and let the inverse design loop over it once more to see if you have achieved the best result already. So we don't really, so far we don't really look at stability, but we rather see that we can make these structures. And of course the structures would look way different if you didn't do this smoothing with this kernel. So in a sense, I guess we don't do it specifically. We rather see that we can make these structures, and then I think we arrive at something that probably does the job like you insinuate. Did that answer your first question? Thanks. On your second question, hold on. Now I was blanking. What was it? Can you just say one word?
Sources.
Sources. Thank you. Yeah, sources. Oh man. Your former group in Göttingen built this one beautiful source where they fibbed components. So it's not really fully integrated on the chip in the sense that you can etch it, but there was a fantastic attempt. And who's working on it? I don't know. I have to say. So we're working on it on different size and length scales with different methods. Ideally, of course, a real nanofabrication group could do it. So we were in touch with some groups in the US. But you know, in nanofabrication, everything that is 3D is really painful. If you require cylindrical symmetry or so, it's a nightmare for nanofabrication. So I'm not so sure. There's not a simple one-step nanofabrication process, but I think it will be a combination. And I don't really know who's really working on it, I have to say. I think this electron optics is so far away from nanotechnology that usually it has to be the electron optics people who basically venture into the nanotechnology. Unfortunately, the other way around would be fantastic, but I haven't seen it.
I can tell you that these sources for the ultra-fast lead you mentioned from Klaus, they are wonderful but very challenging.
Yeah, I can see that.
Very, very challenging. It's like you give them names, because if they pass away, you mourn them.
Yeah. No, I mean, we all know how complicated it is to fit something and to somehow place these components, right? Yeah. I can see it. The fun thing is, I think that's why this entire electron microscopy business is so conservative. The same holds true for these big machines. I mean, the development is so slow just because everything takes so huge efforts. But I think it's worth it. It's a serious problem that we're dealing with, but we should hang on it. And at some point, it probably works better or so. But yeah, I'm pretty aware that these FIP sources are hard to operate.
And it's great to be an innovator in a conservative environment, right? You get to be the one, so it's not too bad.
True. I like that.
Yeah. Our next question is from Tal.
Hello, nice talk.
Thank you, Tom.
Yeah. Do you have any idea what is the efficiency of energy transfer from the laser to the electrons?
That's a great question. And that's the point that the accelerator people always give us a hard time. This is never going to fly, and an accelerator is only a good accelerator if it's power efficient. And very early on, Bob Bayer and Bob Seaman teamed up to tackle that question. So now I don't recall from the top of my head, but I think it was a PR stab paper from maybe even 2008 or so, where they look into this. And of course, it's the same problem. That's why Bob Seaman was ideally suited to do that, or he set to do that. It's the same problem like with all these accelerators. It's basically impedance matching. So you have to choose the right bunch charge for the right structure, so that the light fields are efficiently absorbed, if you will. And they worked it out, and they showed that yes, it can be power efficient in the sense that really a lot of the light, or a lot of the energy of the light, is then going to the electrons. But for this, you also need, like Avi pointed out, like we discussed with Ofer, you need better sources. We have more electrons also in one bunch. Other than that, you could probably try to reuse the laser light. So if you make structures where you don't entirely kill the beam, but where the beam goes through, you could probably just recycle or reuse the light, and probably even just steer it to another part of the structure. But in principle, like Bob Seaman's group and Bob Bayer showed, in principle, this can be power efficient.
Okay, thank you.
Thank you, Tom.
You mentioned Ising, right? Ising 1924 or so?
Yes.
I'm curious, actually, is this the same Ising from the Ising model?
No, there's another one. I also checked. This is, I believe, the one of them was called Gustav, and the other one was called, I forgot, but it's a different one. I also checked. I thought, wow, did he really build accelerators and come up with such a great scaling model?
Okay, that could have been a nice coincidence, right?
Would be cool. No, it's two different people. Yeah. I think they were also not even related.
Yeah. I won't let you go before I ask a question from my side. You mentioned a zeptosecond, and this is, we all look at the record. What would be the best shortest electron pulse possible? And we are even fighting with FV on this right now, but then claiming that there is no way to do zeptosecond and it's not possible. So I guess let me play the referee for a moment and bring the challenge, right? Let's say we want to get to this very short electron pulse. So at such zepto, right, or sub-atto regime, about, for example, whether all electrons or all the electrons, since it's a wave packet, is really moving straight, or maybe that electron is actually having slight broadening, and then the trajectories, the different ones, will delay it a little bit. That could already put a limit that is really hard to fight. So what if it's really the fundamental limit? Do you think we can really get to the Zepto?
So I was also skeptical. Now, the one who did the simulation here is in my group, I think, is Norbert Schönberger. And I'm pretty sure it was with GPT, which is a full 3D particle tracking. So I'm pretty sure this is taken into account. Of course, there's
then you also have the other, yeah.
I'm pretty sure it's only a single plane, of course, right? I mean, it's like a lens where you focus a beam, and the radii length for such a short pulse will become very short. So you really have to hit the right plane where you have this temporal focus. Unfortunately, it's too long ago. He did this more than a year ago. We looked at it. Of course, the question you always need to ask is how many of the electrons are really in the zeptosecond range. Of course, there are some electrons also spread out temporally.
Yeah.
That's always an issue. But there are interesting schemes, pre-bunching schemes, where you use, for example, say a terahertz field and then the optical field to really control the electrons that much in phase space. And what I always find fascinating to see, and this is maybe showing that there probably is no real fundamental limit, when you see what they do in the classical accelerators. So Swissfel has a mode that they call ultra-short mode, or I think they just call it ultra-short mode, where they expect the RMS pulse duration to be below 1 femtosecond, driven with 5 gigahertz or so. So they drive at a frequency factor of 10,000 slower than ours, and they're in the single digit or even sub femtosecond range. So when you scale it down by 10,000, you arrive already at I think 10 or 100 zeptoseconds. So you're far below 1 femtosecond. Once we have the same degree of phase-space control like they have in classical accelerators. Of course, you can always question that. Can the control over light fields be as good as the ones over microwave fields? I don't know, but technologically speaking, I think there is nothing really keeping us away from this. So this I always find very fascinating, that this mode is out, and at Swissfel they don't. That's a fun thing. They can't measure this. They can't measure these pulses with their streaking fields anymore because the streaking is too slow. So you basically they infer it. They know the particle simulation in their case works really well. They trust it. They think they have this electron bunch, but currently they can't measure it. So we hope that with our techniques installed at Swissfel, we can show that these pulses are really that short.
Nice. And GPT is a convincing argument, because we can say, oh, wave buckets or classical simulation, but it does capture this broadening of different trajectories to different parts of the
sure. And all these energy effects, and the fact that, of course, oftentimes people just assume, okay, we just do everything linearly. They don't really take the sine wave into account. Of course, all this you have to take into account. The fact that it's not just a linear field gradient, of course. But I'm blanking, but we should probably dig it out. But I'm 99% certain that we did it in GPT and with all the proper fields.
We have a few more questions. So if you still have the time, I think we have a question from Michael and from Ofer after this. So Michael, you want to go next? Oh wait,
You're muted.
You're muted. Although it doesn't say mute, but something is
something is muted.
Yeah.
Can you hear me now?
Yeah.
Hi, Peter. Greetings from COVID isolation.
Oh, poor you. I'm sorry to hear that.
I have a follow-up question to Ido's question. Isn't there a fundamental wave limit from Heisenberg's time energy uncertainty?
Because you don't even need to invoke Heisenberg. Of course, the energy spread in your temporal focus will be very large, and of course, the limit is Heisenberg. Sure, the smallest energy spread you can achieve is given by Heisenberg. But even already classically, we see with this bunching, right? I mean, when we go here, you see here that this is the energy spread. If you want to make this time and space smaller by invoking maybe larger bunching fields, the spread in energy will get larger. And the smallest spread you can allow is, of course, given by Heisenberg's uncertainty. You're right. But so you will have large energy spreads in your temporal focus for sure. Thank you. That's important. It's very important for some of the applications, because some people then think, yeah, great, we can have zeptoseconds and beautiful narrow energy. It's like, yeah, guys, not quite.
Yeah, I think we estimate
Thank you very much.
KV, right? We estimate a few KV energy width will give us a sub-atom.
Yeah.
That's so it's definitely challenging, but it's within the numbers that are already seen.
Yes, exactly.
Offer, you want to go next?
Yes, thanks. Maybe it's a question I also asked Fabrizio, by the way, but assuming money is not an issue, as you claimed in the SCM business, the situation is, but what would be the ideal machine, right? So what do you want if you get to choose?
Both. I think both SEMs and TEMs are not.
Oh no, within the SEM, within the SEM.
Within the SEM, within the SEM. So you don't allow me to go away from an SEM?
Do whatever you want. Just answer freely. It's your talk.
Point with these machines is they're optimized for oftentimes they're optimized for resolution, right, and maybe even throughput. These lithography machines are also, and great Israeli company that runs a branch in Munich, Applied Materials, has this fantastic machines. Well, actually, John Breyer, the guy who did the demonstration, that's also a fun fact. The guy who did this year, right? Who did the first demonstration? He's now with Applied Materials, close to Munich, working on lithography electron microscopes. And the point is, they're not optimized for any temporal effects. They allow, when you look at these diagrams, they allow large extensions of the electron beams away from the optical axis. So you get huge trajectory effects when you laser trigger your source and then the beam is guided down. And then you always get long pulses. Maybe you don't care, like Avi suggested in the very first question, maybe why don't drive the electron accelerator with picosecond pulses? Then you probably don't care. So it's really the question what you want, what you're after. I still think a kind of optimized, maybe not right away on the chip, but small scale electron source could be extremely interesting. And then there's some very important point, of course. There are these, you probably know, these environmental electron microscopes. They operate, and oftentimes Agilent has one that is so small the electron column is probably only that tall. It's multi-layer based. It's from a company that used to be in the San Francisco Bay Area that Agilent then, or Keysight, now bought. And that's why I've seen it in this little startup company. But they can only generate, I believe, 5 kV electrons. So what can you do with 5 kV electrons? So far it's tough, but we've shown already you can accelerate from, I don't know, 7 kV on or so. So if you had a scheme to accelerate such slow electrons also efficiently on a chip, I think that's the way to go. Smaller, that means we have to put stringent requirements on the laser accelerator side, where we can start with slower electrons. This is also exactly what we're looking into. I think it's very important. Then this puts much less stringent high voltage requirements on your DC electron optics, and then everything can be built much, much simpler. So I think we should approach from two sides, go down in energy that we have to provide with a DC voltage, and then we have a much larger design space. I think that's the way to go. That would be my dream machine. And the source may be already existing in these environmental machines.
I can only say that the environmental machines are sometimes actually the most accessible, for example, price-wise, because they don't invest much in the electron optics. So they say, okay, at least we make it environmental.
Yeah. Are there more than the Keysight one? I'm aware of the Keysight one, but there are more.
Thermo Fisher has an environmental Quattro. Of course, it's a much larger scale, but no buts. I don't remember the highest pressure it can sustain, but you can inject directly into the sample region and so on. Yeah. So
these are essentially operate it in vacuum. I mean, it would even be advantageous for these machines. It's very interesting, I think, Offer, and probably could be very interesting. But then the electrons are so slow that the phase matching is again a little harder.
Nice, interesting.
Thanks.
Thank you.
Well, thanks, Peter. Let's see if there is any final question from anyone in the audience. I'm glad to see that people stayed with us also for the discussion. It was really fascinating. Okay, I think we can conclude, and thank Peter again for both for the talk and also for the discussion after. It was really wonderful. So we'll hopefully meet next time face to face, and
Really
inviting people to Israel. Excellent. Thanks, everyone.
Thanks so much, Ido. Thank you very much, everybody.
Okay,
Thanks for organizing.
Thanks, Peter.
Yeah.
Thanks, Peter.
Bye-bye.
Bye, guys.
Thank you very much.
Good talk. Bye.